So in today's video, we are going to look at the impedance in an AC circuit. The impedance in an AC circuit is the opposition offered by the circuit to the flow of sinusoidal current. Now from Ohm's law, we have V equals I times Z, where V is called the phasor voltage, I is the phasor current, and then Z is the impedance. Now from this relation, we can express the impedance, that is Z, as the ratio of the phasor voltage to the phasor current, and that is measured in ohms. Now even though V and then I are all phasors, Z is not a phasor simply because it does not correspond to any sinusoidal varying quantity. So unlike the situation in a DC circuit, where the opposition to the flow of current is due to only the resistor, now in an AC circuit, the opposition to the flow of current is due to the combination of these three elements. 1, the resistor. 2, inductor. And then 3, the capacitor. Now the opposition due to the resistor is called the resistance, and that is represented or denoted by the letter R. Also, the opposition due to the inductor is called the inductive reactance. And that is denoted by XL. Also, the opposition due to the capacitor is called the capacitive reactance. And then that is also denoted by XC. Notice that all these three quantities are measured in ohms. Now, as a complex quantity, the impedance Z can be expressed in the rectangular form as Z equals R plus JX, where R, which is the real part, is called the resistance, and then X, which is the imaginary, is called the reactance. Now this reactance can either be the capacitive reactance or, better still, the inductive reactance. If X is positive, then what this primarily means is that the impedance is inductive. Thus, X is equal to XL, and that is equal to omega L, where XL is the inductive reactance, omega is the angular frequency, and then L is the inductance. And that is measured in henries. Now, if the circuit is purely inductive, then the impedance of the circuit is given as Z equals JXL, and that is equal to J omega L. Now in that case, the current is said to lag the voltage by 90 degrees, and this is the phasor representation of a purely inductive circuit. So the current lags the voltage by 90 degrees. Now in a case where the circuit is not purely inductive, then even though the current lags the voltage, it's not going to be by 90 degrees. Also, if X is negative, then it means that the impedance is capacitive, so that X is equal to XC, and that is equal to 1 over omega C, where XC is the capacitive reactance, omega is the angular frequency, and then C is the capacitance. And that is measured in farad. Now if the circuit is purely capacitive, then the impedance of the circuit is given as negative J times XC, and that is equal to negative J times 1 over omega C. So this is the impedance of a purely capacitive circuit, and in a purely capacitive circuit, the current is said to lead the voltage by 90 degrees. Now if the circuit is not purely capacitive, then even though the current leads the voltage, it's not going to be by 90 degrees. So in summary, what we are trying to say is that considering an AC circuit which is purely resistive, the opposition offered by the circuit to the flow of current is due to the resistor only, so that the impedance Z is equal to R, and in that circuit the current is said to be in phase with the voltage. 2. Now in an AC circuit where the circuit is purely inductive, the impedance of the circuit is given by Z equals JXL, that is equal to J omega L. Now in such a circuit, the current is said to lag the voltage by 90 degrees. So this is the phasor representation of a purely inductive circuit where the current lags the voltage by 90 degrees. 3. Still considering the AC circuit, that is a purely capacitive circuit, the impedance of the circuit is given by Z equals negative J times 1 over omega C, and in such a circuit the current is said to lead the voltage by 90 degrees. Now the impedance of the circuit, that is Z, which is represented in the rectangular form as R plus JX, can as well be represented in the polar form as the magnitude of Z angle phi, where phi is the phase angle. Now the magnitude of Z is given by the square root of R square plus X square, and then phi is equal to tan inverse of X divided by R. Now if you want to find the value of R, which is the resistance, then that is given as the magnitude of Z times cosine of angle phi, and also if you want to find the reactance, whether inductive or capacitive, then that is equal to the magnitude of Z times sine of the angle phi. So now let's move on as we solve a few examples. So let's take our first example. Determine the current that flows through an 8 ohm resistor connected to a voltage source that is Vs equals 110 cos 377 T. So let's try to solve this together. Now from the question, we are given the sinusoidal voltage, that is V of t, equals 110 cos 377 T. And then we have the resistance of this circuit to be 8 ohms. Now you realize that this circuit is a purely resistive circuit. Therefore, the opposition offered to the flow of current is due to only the resistor. Hence, we have the impedance Z also to be equal to 8 ohms. Now from the relation V equals I times Z, we can have I equals V over Z. Now let's input the values of V and then Z. So for V, we have 110 cos 377 t divided by Z, which is 8. And that gives 110 divided by 8 is 13.75. So we have 13.75 cos 377 t. So this is the value of current that flows through the 8 ohms resistor. Now in the previous lesson on phases, we saw that a sinusoidal voltage or current can either be expressed in the sine form or in the cosine form. Now for this question, we had the voltage in the cosine form. Now you can also choose to convert this signal from the cosine form to the sine form and then work with that. So let's look at how we can do that. So using the trig identity, that is cos omega t equals sine omega t plus 90. In that case, 110 cos 377 t becomes 110 sine 377 t, and then we add 90 to the phase angle, so plus 90. So this is the value of V of t. And then we have I equals 110 sine 377 t plus 90 divided by 8, and that is equal to 13.75 sine 377 t plus 90 degrees. So you can either choose to work with the cosine form of the wave, or better still, you can change that from the cosine form to the sine form. Now each of the answers obtained here is correct. Now let's move on to the second example. So to example 2, what is the instantaneous voltage across a 2 microfarad capacitor when the current through it is I equals 4 sine 10 to the power 6 t plus 25 degrees? So for this question, we are going to find the voltage across this capacitor. Now the voltage is given as the current times the impedance according to Ohm's law. Now we are given the value of the instantaneous current to be 4 sine 10 to the power 6 t plus 25 degrees. And then we are supposed to find the value of the impedance, so that we multiply that by the current to get the value of the voltage across the 2 microfarad capacitor. Now looking at this question, you realize that this circuit is a purely capacitive circuit because we have no value for R, neither do we have any value for L. Therefore, the impedance of this circuit is given as negative J times XC, and that is equal to negative J times 1 over omega C. So let's substitute the values of omega and C in here to find the value of Z. Now from the question, we are given the value of the capacitance, which is 2 microfarad. So 2 microfarad is the same as 2 times 10 exponent negative 6 farad. Also for omega, comparing this current, that is this sinusoidal current, to the general form of a sinusoidal current, given as I of t equals Im sine omega t plus phi, you realize that omega is equal to 10 exponent 6. That's comparing these two equations. So we have omega to be 10 exponent 6. Now let's substitute these two values into this to find the value of z. So we have z equals negative j times 1 over, in place of omega we have 10 exponent 6 times the capacitance, which is 2 times 10 exponent negative 6. Now let's simplify this. So we have negative j times, now 10 exponent 6 cancels out 10 exponent negative 6. So we are left with 1 over 2. And then 1 over 2 is equal to 0.5. Therefore, we have z equals negative 0.5 j. Notice that this value is in the rectangular form. Now let's try to convert this to the polar form. So when you do that, we are going to get 0.5 polar negative 90. So this is the value of the impedance. Also, let's convert the sinusoidal current into the polar form. So that is giving us 4 polar the phase angle. So that is 4 polar 25 degrees. Now using V equals I times Z, we have the voltage across the 2 microfarad capacitor to be equal to the value of the current, which is 4 polar 25 times the impedance 0.5 polar negative 90. Now to multiply this, first of all we are going to multiply the modulus, or better still the magnitude of Z, so that 4 times 0.5 is 2. So we have 2 polar. Now to the phase angle we are going to add them. So 25 plus negative 90 is negative 65. So we have the voltage to be 2 polar negative 65 degrees. Now we are asked to find the instantaneous voltage, that is V of t, across the 2 microfarad capacitor. Therefore, we are going to convert this voltage from the polar form back into the time domain form. So we have V of t equals 2 sine 10 power 6 t minus 65 degrees. So this is the instantaneous voltage V of t. Now let's move on as we solve the last question for today's video. So in this video, our focus was directed towards a purely resistive circuit, purely inductive circuit, and also a purely capacitive circuit. Now considering this example, we have a series RL circuit. Now in the next video, we are going to look at a series RL circuit, a series RC circuit, and also a series RLC circuit. Now even before that, let's try this example on this RL circuit. A series RL circuit is connected to a 110 volt AC source. If the voltage across the resistor is 85 volts, find the voltage across the inductor. So how do we solve this example? Now let's represent the information given in a circuit. So we have the source voltage to be a 110 AC source. So this is the AC source, 110 volts. And then we are told that the voltage across the resistor is 85 volts. And we are going to find the voltage across the inductor. Now because this is a series RL circuit, the resistor is connected in series with the inductor. And we are being told that the voltage across the resistor is 85 volts. And we are supposed to find the voltage across the inductor. Now because this is an AC circuit, the voltages here are phasor voltages. So because the voltages here are phasors, the square of the source voltage is equal to the square of the voltage across the resistor plus the square of the voltage across the inductor. Now let's transpose VR square to the left hand side. So we have V square minus VR square equals VL square. So we have VL equals the square root of V square minus VR square. Now we have the value of V to be 110 volts and the value of VR to be 85 volts. Therefore, let's substitute these values here. So we have the square root of 110 square minus 85 square, and that gives 69.82 volts. So basically, this is the voltage across the inductor. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.